All right. I'm going to talk a little bit more about this. I know it's exciting. This little manifesto business. You're making up for yesterday? You guys aren't on Facebook, are you? Really? You don't, no one uses Facebook, do they? You can admit it, I guess.
What's that?
Instagram. Instagram, yes, sort of. Yeah. All right. Anyway, the world fell apart yesterday, right? There's an old Onion article about the internet going out and just massive amount of work being done as a result. Productivity. All right, people, let's go. All right. Okay, so we talked about this the other day. I stuck this in the end, but I guess I'll lead off with it just to finish it. I didn't have this, so this is an important object. So just put up with me for a second. Is it spelled right? Yeah. Okay. All right, good. Okay, so we had this story, and we looked at this rather interesting thing that you are made out of. Not many things, right? 29, basically, little bits. Oh, yeah, I tried to. It's not enough, is it? All right. Is that dim? What's that dim? These are some funny lights. Okay, all right. How's that? Yep, good. It is better. Okay, we have some sulfur inside us. That's the evilness part. Okay, all right. So I have just a couple other pieces here, and then I'm going to have this one-page story for why we're doing complex systems. Right, it's hard to deal with people when a tiny part of you saw them as a temporary collection of atoms that would not be around in another few decades, right? So we tend not to think of that when we talk. Well, people do think of other people as things, and those people are not good people, but don't usually think of it at this level. I think I have a.
That's because losers look stuff up while the rest of us are carping all them DMs.
Listen to your sister, Morty. To live is to risk it all. Otherwise, you're just an inert chunk of randomly assembled molecules drifting wherever the universe blows you. Oh, I'm sorry, Jerry. I didn't see you there. How much of that did you hear?
All of it. You were looking right at me.
Okay. Oh, what a joy. I couldn't believe it when I saw that. Okay, so not in any way endorsing Rick and Morty. But anyway, all right. So a little bit of a history then, right? So this is going back in time. Adam, it's one of these good things we managed to not name after someone. We named it after using the words. So to not cut, right? So this is Democritus's idea. Obviously many people who we do not write about anymore because it's not written down, thought about it, looked up at the sky or something for thousands of years. But Plato was upset, apparently wanted all of his books burned, is the story, but it is passed down, but said, look, all of these things around us are made up of tiny little pieces. So this, that's microscopes, you can't get it. It's a weird conception. Anyway, so that's a long time ago. A couple of thousand years later, we start to get to the chemists blowing things up, doing crazy things. And the idea of so what will become the periodic table emerges from all of this, right? This understanding that there are these pieces, a lot of effort goes into alchemy. Newton, I think, was involved in that as well. I mean, everyone's trying to turn, lead into gold. Why not? Why not? Maybe, right? I mean, maybe. So this is sort of going on for a couple of hundred years, and I would call this sort of 300 years of, this is just my view, Golden Age of Reductionism, right? So this is this incredible time in science where we are figuring out there are these little pieces inside of other things, and then we're kind of getting down to the limits. Yes, there are quarks maybe, but the atoms was a very incredible realization, achievement. And so then you get to, and so this is to give you a sense of like, we are not very far into, and we're generally pretty stupid, but we're not very far into understanding some really basic things about the universe and the world and so on. And so Boltzmann, a bit of a, he was a sad existence in there, a depressive fellow. He went through different states, but he built a whole gas theory out of this, starting from first principles, thinking of little things bumping around off each other, right? So that's an idea. You can imagine this sort of billiard ball game, and there's still zillions of papers on quantum billiards for some reason. But others around him said, no, we don't like you. This is bad. This is a stupid idea. Mark, who, of course, we named things after, we've named, Boltzmann's got a constant. That's pretty big. Mark is Mark. There you go. Yeah. Thank you. Anyway, so, and apparently, so, and again, this is legend. So this is in 1904, he's at a conference, and physicists really rejected the concept of atoms, right? This is 117 years ago. And they're like, no, that's not true. You guys are mad. Planck came up with, the quantization, but just did it as a mathematical contrivance, which is interesting. That can happen, but still thought it was wrong, right? But it worked. So he wasn't invited to physics. I mean, he's incredibly famous now, of course, but he was stuck in a section called Applied Mathematics. Attack philosophy, and then blah, 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 going on about Lamarck. He thought Lamarck was kind of okay. But anyway, right, blah, blah, blah. But the past was, but that's fair enough. He's attacking science for not evolving, right? It's true. It's still true. It goes on forever. Yeah. People get really stuck and flock around ideas and they can't help themselves. It's been funny to be part of that, I think. Okay. All right. Eventually we get it right, but gee, it is a struggle. So that's 1904. And look, Boltzmann takes his own life. I mean, this is a terrible, end to his, things don't work out for him. And he's, from what I understand, yelling and screaming about, not exactly, but people would not listen to him. So then we have Einstein, who had a bit of a burn for a year there, sort of these 5 amazing papers. And one of them is about Brownian motion. So you've done this, right? Random walks. Random walks is a Brownian motion story, right? Diffusion. And so the idea of Brownian motion is the 1800s, again, named after really a special name, Brown, who noticed all these little things jiggling around, and there's kind of this idea of diffusion. And Einstein's paper is, it's like a little, let's imagine things statistically bouncing off of each other and so on, right? We're not actually going to have particles hitting each other like billiard balls, but just try to do something more statistical and end up with a Gaussian, right? Derives a Gaussian out of that. So that comported with observation, this sort of general observation. Let's see if I can get this paper. So rude. I'm not saying all these people are good people, by the way. No, that's funny what it did there. I think I should have the paper. I want the paper. Yeah, here it is. No, don't have it. All right. This one. Will that work? Okay, good. Yeah. Right, so this is at least, I think, a translation from the original one, but yeah, little differentials here, and eventually you start to see, I think, and we don't have to go through this too much, but so this is a diffusion equation, and I think you should get to, look at this, there it is, diffusion equation. It's a classic equation. And there it is. This is a Gaussian, like you guys found for just simple random walks. There's the root t, and time again, right? So they're the standard deviations. There's a diffusion, constant diffusion, which scales things. So that was an incredible achievement. Of course, we think of Einstein doing everything apparently in a vacuum. It's not going backwards like I want. Anyway, but lots of other people were thinking of things and getting like special relativity, right? This sort of scaling, and the Lorentzian is Lorentz, right? Anyway, okay. So this is so the big story here is he says if we had an atomic model, things bounce off each other, then we get this Brownian motion, this Gaussian, right? So this is this is a microscopic story giving rise to a macroscopic behavior, just like random walks. If you've watched Squid Theory, there's a Squid Game. There's a bad moment for random walks in that. But anyway, so again, this is something we're really engaged. And this is a Milo kind of story. It doesn't give you, it gives you a mild out behavior still, like, but it's a, you know, it's like, these are just little things bouncing off each other, and we get a nice macroscopic thing. We're excited, you know, to the extent that we can explain the world in this way, we will do it. It gets much harder perhaps to, you know, say, okay, let's have a few species bouncing off each other, and here is the Amazon. Like that's hard, right? So we can't do that for everything necessarily, but the things we can, we absolutely have to lay out. And then there's an experiment that appears in 1908 that verified this, right? That actually said this: we have theory, we kind of have this macroscopic description, and then it got at how things are really sort of moving around locally. And that so this is 4 years after Boltzmann was told to go and play with the mathematicians, not even the real ones, the dirty applied ones. They're like, okay, atoms. So that is not long ago, 113 years ago. And of course, then you have DNA. It's the middle of last century. You know, you start to get to this, which is a different thing again, right? But it's still like, here's a code story. You know? And I guess the way I think about that sort of the arc of the universe is, yeah, physics, randomness, all this stuff smashing around. Eventually you get to these balls around other balls. Life starts at some point, and then it's algorithms increasingly as you go up. Except for yesterday when Facebook was down and people were sad. Well, actually, people were sad and happy, right? I mean, there was a mixture. Yeah. Twitter was enjoying itself. These really don't seem to have been used in any way, do they? What is in here? Oh, that's ironic because they're on the floor. They're supposed to be on. Yeah. So I'm a bit hobbled because I told you about the Australian rules football thing, but it turns out to be not a great thing to play when you're young. Okay, so okay, so this is Feynman, who, you know, large brain. You know, stories are a bit funny about him, I guess, as a human interacting with other humans, probably unsurprisingly. So I don't know, but a bit of a celebrity character, and I don't know, maybe not that well known. Einstein is Einstein, right? Mona Lisa kind of thing. But, you know, in terms of physics, incredibly famous. So basically, you know, if everything is destroyed, what would you pass through? Well, apart from don't watch Lost from the beginning. I'm sure there are a few other things we could put before this. But anyway, he's going for the science stuff. So it's a atomic hypothesis that all things are made of atoms, or Game of Thrones, not good. So, right, little things that move around, bouncing off each other. It's a pretty good sentence, but basically, you know, that we're made out of tiny things, right? Enormous amount of information about the world, and as we sort of laid out, it took a couple of thousand years to get there. All right, so let's just have one page. So there are systems everywhere. Some of this will seem, I don't know how you think about this, but it does seem to be something that I have to explain. I feel compelled to explain over and over. People maybe, you know, anyway. So a science of complex systems. It doesn't mean there's a universal theory. It just means that this is the phenomenon, right? Systems are everywhere. There's this property of emergence, which matters. So it's not a simple thing to understand them at all, as it's pretty obvious. So this is what happens to science, right? We've had 300 years of this golden age of reductionism. I mean, getting to DNA, you know, understanding viruses are viruses, right? You'd think that it has helped us. It has helped us. It has helped us. But we know there are viruses, and we know we can build these little machines that, you know, fight them, basically. The story part is much harder, as it turns out. But you know, that's a different game to, you know, 1918. Completely different game. Different game to, you know, 1600s in Europe, when who knows why these things happen. But golden age of reduction, we're really struggling still. As I said, I pointed to stories, but, you know, how people interact with each other. This is a very ongoing, you know, that research will continue forever, presumably. But you know, social psychology is in a huge upheaval. All these experiments don't seem to have been held up over time. But, you know, we've got some of these pieces. We've definitely got atoms. Yes, we have quarks. Maybe we don't really need to worry about them too much. But So basically, understanding these natural systems, the ones we create, is this huge. This becomes the game of science going ahead. You get to create new atoms potentially, right? Little building blocks that interact with each other. That's an incredibly enormous, interesting part of what we might be able to do with science. I mean, chemists are always trying to do things that may help the world or not. Everything to do with code. There's all these little interacting pieces, all these little, like Instagram is some interacting, you're all these little agents interacting with each other. What happens with that? Good and bad things, right? So how do you create systems that are creative, good, helpful, safe, robust? I mean, the Constitution, right? That's another new rule set. The U.S. sort of emerges, right? That and says here's a little rule set, and let's build out from that. We potentially get to do that again and again. So there is this enormous thing that comes out of physics, just observed in many different places, which is universality, right? So there are systems with these that may have quantitatively different microscopic details, right? So air and water have different components, blood different components, but they obey the Navier-Stokes equation. And that's remarkable, right? That's remarkable. There is no reason, I think, beforehand, I mean, if you go back thousands of years, that you would think there would be mathematical equations, even if you kind of understood what that was, right? I mean, it took us, it's only 500 years that we've had an equal sign, I think, right? So that we would understand we could do that. We'd have calculus. We'd be able to describe something like the flow of honey or water with an equation. And then if we kind of got that on board, that those equations would be the same one. That's not obvious at all. That said, I do want to kind of say this again, that I think at some point, math does an incredible amount of mapping of the world, but there's a lot of math that doesn't, and it's unclear, like, how we get to the really complex system stories if it's more just like counting and modeling and making simulations, right? So I think we're sort of leaving behind partial differential equations when we get into the more algorithmic phenomenon. Okay, so, but this is a big deal. So universality, so they have different microscopic details, but they can behave macroscopically in the same way. And being able to sort of talk about this, people, of course, thought about systems for a long time. Often it's been pretty abstract. I mean, again, Constitution, like this is a way to make a system, like a social system, work. Write down, let it run. That's a big plan. Marxism, these are big sort of plans for how to run things. So, people have done pretty sophisticated things way before computers. There's no question. Built big cities with plumbing and stuff. But we can measure and record all this stuff, all this data, curate it. This is very difficult. This data wrangling part is very difficult, but we can put it somewhere and visualize things, do all this kind of work. So and I like to talk about fields going from data scarce to data rich, right? This happens slowly over and over again, right? So astronomy is about 2000 when they go from individual, sitting there through a telescope, counting, hoping it's not cloudy, to having arrays of telescopes and then having and so on. And then it becomes like a massive data problem. Changes how or it expands what you can do. It doesn't wipe out, the small scale stuff as well. The thing that might take one person, that's all still there. Same with social sciences, interviewing people, doing that sort of thinking, whatever. That's all incredibly important. It would never go away, but now you get to a kind of a remote sensing aspect to it, like a big thing. Ecology, right? So we can see some things from space, trees, how things are, wetness, all sorts of pieces like that. But we don't know where that nematode is or, what it ate yesterday, right? That's a harder thing to do. So that's measurement. And then, of course, we can do the simulation model, complex systems in great detail. And this is a really big battle. I mean, we'll see a couple of examples. The thing I want to start talking about today, Simon's model is rich-get-richer model is exactly one of these simple things. It doesn't need big computational stuff necessarily. But we've got deep learning, we've got all sorts of tools now that kind of bypass traditional ways of thinking about things. And you'll see different fields. They'll turn up and say, no, we have to have a theory before we do anything. We're not allowed to have, apparently we have to understand everything in a box before we go outside, and it's a big smush to me. Like there's looking at stuff, trying to make up ideas, testing it, making experiments. Yeah. Anyway, I think I have some examples for that later too. All right, so that's one page, and that's what I feel I needed to confront you with at some point. Probably at the start of the semester, but I did not. All right, so there are two more, I guess there are 5 parts to this, I suppose, but I sort of have 4 named, 1, 2, 3, and 4. So we did random walks, getting these parallel size distributions for the first return story, transformation of variables, which is not very exciting, but it is definitely a source of these things. And then I've got a couple of pieces here. One is a model, as I said, it's a rich-get-richer model, Simon's model, which is going to be an incredibly simple model, right? And we'll see it gives us a lot. And then Mandelbrot appears, and we'll see how they have a big argument with each other. Actually, plays out in a time well before TikTok, in an amusing fashion. And Mandelbrot's like optimality, right? Like systems get to some point, they get to these kind of edges of where they are because of optimality, right? Something's being maximized or minimized. Something is happening like that. So there are iterations through evolution that produce these systems that are kind of have these parallel tails, which, A, we're interested in because we observe them, and then B, they allow for catastrophe, right? We're very worried about them. Both, they're real, but they have this kind of, if they were benign things, it'd be like, okay, fine, but they can explode. All right. Oh, the outline doesn't work. Okay. Gotta have a bug article. So, rich get richer. So this is a really fundamental thing, and you can see why you have to have tax laws, unless the brakes come off. And South Dakota apparently has all the money, which is strange. But that's the basic model: rich get richer, right? And it's often referred to as Simon's model. You'll see preferential attachment when we get to networks, which is an okay term. I will argue about terms, of course, because I like to do that. But I like this one, the rich get richer, and we'll sort of inspect that wording as we go in. But the idea is, yeah. So if you're ahead at some point, you get further and further ahead, and right. So there's going to be this differential, deeply understood by humans. This is why the cheating occurs, right? The bluffing, the lying, because you want to you want to pretend that you're this one to start with. Right. Okay, so as I said, random walks we started with, that's a additive aggregation, right? So there's the one thing about random walks that you needed to remember is just where you are right now, which should be something you know, right? And then you would take this step. But we were also comparing that walk to many other walks. They're not interacting with each other. There's just this whole ensemble of walks, and we think about this big soup of them. They're all independent. So that's obviously not what's happening if we're thinking about, say, cities competing or corporations competing or words competing for usage. So there's random addition and subtraction, simple memory. As I said, we're comparing across realizations. They could be in parallel if you like, but they're not interacting with each other. There's no competition. So this is going to be a random additive thing. So there's it's going to be more like copying, but it's adding. We're just sort of adding one, right? So if we have, a city with a population, we add one person to it. That's adding. But we could think of words. We have the word the or Moby. Moby Dick. Right? Moby's appeared so many times. We have another one. You can think of it as like a copying thing. This is not how you write books or how cities grow necessarily, but it is a very simple model that we can start with and then kind of maybe try to modify to represent behaviors or to try and capture what's going on with real systems. This won't be about networks yet, but it's basically reinvented, not as well, as it turns out. 40 something years later. So lots of things that become big things, are discovered in many different spaces. That's fine. But it took a while, and it's only the last 20 years where that sort of got glued together. All right, so I mentioned cities, words, what was called the web. This is an odd business, right? It used to be, of course, the internet, which was 1969, 4 things connected together, the ARPANET. That becomes known as the internet. The web appears in 92. World Wide Web, I mean, we still have the www. If you're from Pittsburgh, it's www. So, wash the cars. My wife's family is from there. So, okay. So, popularity, this is enormous, right? So this is, of course, people in themselves, anything, any cultural artifact, you know, why is some like metal rabbit selling for 100? Well, I guess it's money laundering, but there's some weird things happen, of course, when we get at the cultural things. It can be reproduced easily, and with people, in a sense, you can, right? Because your image can be reproduced. Music, great example. All right. So we're going to have competition, and we're going to have emulation, copying. So these are very basic kinds of evolutionary mechanisms. All right, we don't need to worry about this too much, but the point is there are different mechanisms that give rise to these parallel size distributions, and we should worry about them. All right, so we have some history. This is for before zip comes along. So again, these things could have been named the Estoop law, or Estu, or someone from the 1800s. But this is interesting, looking at stenography, right? So shorthand, which people don't have to worry about so much anymore because this is done by hand. Lots of different names for it. Tachygraphy. So this is, of course, a system of writing that's refined over time, and you could start to see word frequency in it, and you could start to think about how long are these pieces that are trying to represent something that appears frequently. Morse code is another example. All right, but that's a word frequency thing based on data from stenography. Then we have this is city sizes actually. So this is again 1910s, and so just what are the population of cities, doing the rank thing that we've talked about. So none of these names really stick in the literature. Like they're there, but they're not really famous. So we have Yule coming along. This is 24. Completely different thing. So the number of species per genus, right? This is, of course, pre-DNA, pre-all, so, all of that kind of world of creating evolutionary trees in smart ways. And so this is hand done, these assignations of species to genus, just the whole concept. King Popeye can order fresh green spinach, I think it is. And starts to think about theoretical mechanisms, like just, how you might get there. And so that is informative to Simon's model, which is a bit we'll get to. Lucca has a bunch of different results. This is goes into bibliometrics. So these kind of basic things like number of papers per author. And 100 years later, people are having a great time with science of science. Just keep, because the data is just so rich now that people have been able to find some really some interesting patterns. I would say in how science is produced. It's a bit of navel gazing, but look, it's an important thing. So I think the most interesting thing that's come out of that, if you take people's careers, and so people will publish, over some period of time. That period of time you have to kind of think about. It will vary for people. Some have long careers, and you have short careers. There's the one-hit wonder kind of thing. 0 is the most number of papers that most people publish, of course, and then you have 1 and so on. But if you kind of then renormalize them and squish them all together and say, look, here's a career, where's the most cited paper in a person's career? So what do you think? The beginning, right? And this is this is used to destroy people's happiness when it comes to mathematics, right? That all good math is done by white men before they're 20, probably. Would be the framing now, I think. They usually leave out some of that. But it's usually, it's done when they're young. I mean, part of the problem is number of those famous people from a long time ago died in a duel at 30, or got hit by a ping pong ball or something because sports was not their thing. Or this certainly shouldn't have done any dueling. So it's hard to get a little bit of a story. So it turns out it's random, and this has been observed by a couple of different groups who also don't like each other. So I feel like it's somewhat stable information. Like, so it, if you have a 30-year career, your most cited paper will be, anyway. So that I like that result because if it's true, it's fine, right? It gives you hope, gives you reason to keep pushing. It was good. And because the sort of presumption was not this, right? The sort of thing that's floating around, which was automatically said here, is that it's straight off. Now, this model we're talking about, we'll get at that a little bit, because one of the problems is, of course, if you have something that takes off, your first paper for whatever reason is huge, and maybe you got yourself connected into a nice venue, powerful people, blah, blah, blah. It gets published in Science or something, and it's a big hit. Like, it really is something new. We'll see that in this course. Some of those papers, things have cited. I know I showed you Tversky and Kahneman, but which are good examples. Hundreds of thousands of citations. But certainly in the last 20 years, work around networks is a good example of papers cited 30, 40, 50,000 times. That's when a field has been created, like a huge new sort of space has been opened up. All right, so that's a nice detail there. Just rich amounts of data. So now we have zip, and I know I've mentioned zip. So this is this book. We looked at some of the examples. Mandelbrot. So Mandelbrot's piece is this optimality story. So we'll get to that. So that's actually 53. Simon is 55. This is published as a chapter in a book, which I managed to track down eventually. This is in Biometrica, which I'm sorry about the citations, but I'll get them to work. We'll go. This is what we're going to go through, and you can work through the model in a couple of different ways. De Sola Price. These are important papers. 65, 76. Started to look at networks, right? So this is the first time, from what I understand, that people are starting to look at networks. This is clearly a case where lots of graduate students were deployed into libraries and had to count things. So some pain there. But these were not totally obscure. Certainly they're now well known, I suppose, as well. But one of these is published in Science, right? It did rise to a real. These are not sort of obscure papers that later on we've obscure. And I don't mean they're obscure for the wrong reasons, right? Because it turns out this was like a piece of gold, right? But in this case, they were sitting in front of people. And then we have Barbazi and Albert. And so Reka Albert. And Barbazi is a very, very famous character in all of this. Many famous people. So World Wide Web was, as I said, what we called it. Now we sort of just call it the internet. That's what I was trying to say before. And networks in general, they have some funny ones. There's the power grid doesn't quite hold up. They have, do they have the active graph in that one? Maybe. All right. Anyway, we'll get to it in a little while. So Herbert Simon, just to tell you about these humans. So it was a political scientist, but actually was really much more spread out, right? So did a lot of things. I think had 1,000 papers. Was definitely in the economics world and came up with this sort of economics-y kind of terrible terms that economists seem to like, network externality. It's like, just what? Anyway, I think it's very, not that any field necessarily does it. The mathematicians have hairy billiard ball theorems. Bounded rationality and satisficing. And so these are important concepts. This is trying to draw away from the economist's mad pursuit of the impossible species, the fully rational one. And this is like, well, sometimes people just say this is good enough. Like they in choosing, there's the optimizer. These people absolutely exist where they have to test everything, blah 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 blah, and drive. Of course, in a day and age like now, it's a terrible kind of blight to have that in your mindset, because there are a billion things to compare. And then satisficing is just going to be like you find something that exceeds some internal bar that you've had, right? You've said, okay, when I get to this, it's good enough. And those people obviously exist too. They're just like, oh, let's get on with it. Bounded rationality, it's like, yes, people are sort of smart. There's a limit. They can't know everything. Blah, blah, blah. 1,000 papers. But yeah, so he's definitely an important person in the sort of the history of complex systems. I think he got himself a Nobel Prize, which sometimes is weird. The economists will give them to people that probably, So knocking out 400,000 citations. So a little bit of a decline, but he's still going along. Just kind of monstrous levels of things. Anyway. And a number of these are books as well, right? So he really produced some enormous things. These are clearly, it's not really crossed out, is it? But these are the same, I think. Yeah. Okay. Herbert Simon. All right. So he's at CMU too in Pittsburgh. Which I said, this is a little anecdote, which I said, well, it's okay. My wife's parents are from there, right? So for a little while, they lived right next to the CMU campus in this building that had these kind of funny elevators, and it was a small thing, and they knew this particular person. They just sort of moved in, and so my mother-in-law gets in the elevator, and there's this fellow there, and he says, "Oh, I'm Fred Rogers. Welcome," and he said, "Welcome to the neighborhood," which is kind of hilarious. Anyway, next to Shenley Park. All right, so let's make a little model. So here's a really simple little model. I've given you the simplest. I mean, purposefully, I'm trying to give you these really simple things because we need to understand the most basic bedrock kind of little models. And if they give us something interesting, that's a huge deal. And this certainly will. How am I doing? All right, so it's possible I said elephant once, and so I changed it to elephants. But it could be elements. Let's have colored elephants, and I won't be able to say the right thing. All right, so this is so think about how you could code this up. So you start with one elephant. You could start with 0 if you want, right? And just at every time step, so there's a clock. This is tick 0. Okay, so we're gonna have boxes. So it's not a random walker. We're gonna have boxes, and I'll draw it on the board, I guess. But we're gonna have boxes. So the clock starts at 0. There's nothing, and a time step it goes to 1, and then an elephant appears here, and it's got some color, right? Okay, so we're underway, and then at time 2, 3, 4, there's just a clock, and you can mess with that. You could make this probabilistic or something. Lots of other ways, but we're going to keep it very, very simple. We're just going to have a simple clock, and of course things are coming into being. Time is unfolding. So we're going to have 2 things that could happen. Probably row. We're going to create a new elephant in that next plot. They're going to be looking at each other with a new flavor. That's not good for elephants. Let's say color. I'm not saying you should eat elephants or that elephants are tasty. Kind of chewy, I imagine. Okay, so what tofu elephants? I guess one mock elephant soup. 1 minus row. So that's probably row. This is going to be typically kind of small, but in principle can go from 0 to 1, right? So it could be with probably 1 that we have. So the limits would be there's a new elephant with a different color every time. So you have to really work through the Pantene or whatever it is. I've got that wrong.
In the homework when it says to code up Simon's model, he mentions 2 assumptions. One of them is this, but the other one is something else.
Okay.
Like, did you mean for us to go with exactly what he says, which is more confusing in my opinion, or this, which makes a lot of sense?
Yeah,
okay,
yeah.
Cool.
Well, let's see, and we'll sort out what he said. I mean, I guess I've read that paper a lot, but maybe I've forgotten what.
I could also be looking at the wrong paper.
No. Yeah, it's JSTOR. Yeah, first of all, can I just say, this is a terrible title. I know I'll come back to this, but this is a dreadful title. There is nothing interesting in this paper. I want to tell you with this title that this is a boring paper that doesn't tell you, yeah, it's terrible. All right. least it's not a question mark. All right, so, I mean, yeah, wow. Anyway, so so we're going to create a new one, and with probably 1 minus rho, we're going to look back and randomly copy from one of the elephants before. We're just going to randomly copy it and put it in the next box. So this fits into this whole, it's very old terminology now, it seems goofy, but urn models, URN, like urns, which I think people mostly think of being related to cremation, which is sort of a ghoulish sort of framework, but you know what mathematicians are like. So, but the idea is you have urns with balls in them, right? Different colors, and maybe there's infinite balls. Maybe this one has 100 red ones, and this one has 100 black ones. And you say, you have little games. Like if you pull out a black one, like, or they're all mixed up. There are lots of variations on these urn model problems. If you pull out a black one, what's the probability that it's 50% or 30? All sorts of questions you can ask. There's fun things. So we can think of this as a kind of an urn model problem where, well, we have one big urn, and either so it's just enormous, right? It's got at time t, it'll have t balls in it. If we think about colored balls now, not elephants, and they're just in there. And then the next time step, we're going to just make a new ball. We haven't with a new color and just throw that in. But with probably 1 minus rho, we would just rummage around in it, pull out a ball, and then make a copy of it and put them both back in. That would be our model here. Now, this is types and tokens. Again, just to use that story again. So types are the species, tokens are the individuals of that species, types are the words in the dictionary, tokens are going to be the words in the book, right? They're the instances. And types more abstractly are like, the word the, like it doesn't have to be in a dictionary, it's just like the word the, it's a type. So we're going to start these, because these elephants are tribal things, they'll start to form groups based on their flavors. All right, well, could get bad, but humans would do that. So this is a mutation innovation thing. This is a very simple sort of instantiation of an evolutionary process, and this is replication. Again, very, very basic kind of aspect. And you want some balance of this, right? If rho is 1, then it's all innovation, and if it's 0, you're not reproducing anything. So this is dialing between, this is the political spectrum, basically. Yeah.
For the replication and limitation, is that choosing from the set of all existing elements, or is it just the actual population that's there? So say like we have 2 purple elephants and 1 yellow. Are we still choosing? Like, is it a 50% chance?
Yeah. Okay, so that's it, and I'll try to make that really clear. So this is this difference between the groups and the actual individuals. So you're choosing from the individuals.
Okay. So
it's very simple.
Yeah, the probabilities that you're going to have for each element are going to change as you're adding elements.
And they are in a funny way, because each specific one could be randomly chosen, right? So what happens is you start to, so here's time, and you can just think of an array like this. So you'd have time, 1, 2, 3. And so this color could be, the first one is yellow and then blue, right? Because we innovated here, and then we copy, and then maybe it's a copy, right? So this is innovation, this is replicate, innovation to start with. So this is replicate, so one of these. 50-50. Let's say we get blue. Maybe the next one's replicate again. It's a third, a third, a third. So that's really important. It's true, at this point, we have 2 blues and 1 yellow. So if we're choosing from type, but we're choosing tokens. So so in here it's going to be 2/3 blue, 1/3 yellow. So this is tokens. And at this point, the types we have, there's the blue elephant group and the yellow elephant group. These are types. Okay, so I'm going to keep saying, because it's a really important thing. Yep. And that's why this also makes this incredibly easy, because if you just have a list, and the simplest thing to do in code is just to call these numbers. It's going to have a lot of numbers, but you can call this first group 0. this next group is a 1, next group is a 1. So we'd have, so instead of yellow, you could do it 0, 1, 1, right? And then later on, you just count up how many 1s you have, how many 2s you have, how many 3s you have. And it's by far the simplest thing, because then, of course, when you want a new group, you just add to the number of different groups you have, and you say that's the type of my new group is 7. Okay, good. So words appearing in language, right? So they appear sequentially. So this is weird. This is a weird way to write a book. So they appear sequentially, right? We're halfway through Moby Dick. With probably Roe, so Herman Melville, he's out going crazy, I suppose. And with probably Roe, just goes back into the book and randomly chooses a word and copies it. No compiled list or anything, just looks at the big thing and just goes, that one. And with probably 1 minus Roe, you just choose a new word, which Herman Melville seemed to do a lot. Lots of things with hyphens. So this is, again, mutation innovation, and this is replication or imitation. Right. So a terrible way to write a book. Yep.
So in general, is Roe variable, or is it constant versus a problem?
So good question. So we will do it so we fix it from the start and figure out what happens if Roe is this value. But in terms of actual simulations, other kinds of versions, you could make it drift, right? And so that would be interesting too. If it stabilizes at some point, then to some extent what's happened before won't, kind of gets carried through, but it's the tail gets just defined by that long-term behavior. What we'll show in here, and maybe if you've looked forward, you'll see, is that because of this course, eventually in doing simulations, it turned out that there is a kind of mistake in Simon's. I'm going to say Simon's analysis. I suspect there were 10 graduate students as well, but so there is an error. So it turns out there's a first mover advantage in this, because if you've got a really low probability of innovation, so it's lots of replication, whoever's first, let's say it's 0.001 chance, right, of a mutation, very low. This one gets to last for a long time. They get replicated for ages until, maybe it's a 1 in 1,000 chance. So typically like 1,000 yellows, and then you'll have this mutation. But then in that next time step, it's got an enormous number of yellows to choose from. So when you go to replicate, it's just pretty much going to, you expect to copy that first one. So that first one just gets to really burn in. And the first mover advantage can be really enormous. And we certainly talk about that in corporations. We talk about it in all sorts of spaces in the world. Okay, so here's an example, and this will help again, hopefully, this is where the story is so far, right? These are the words that have been used. And if the next word is a copy, then we don't evenly choose from these groups. Yeah, each one gets a 1 over, there are 21 words. Each one has a 1 over 21 next to it, and you choose from that. And so as a result, ook is going to be 6 over 21, and so on. Okay. There are different models where you start to say, oh, the group matters, right? I'm going to choose from this. So this is, the analogy here might be cities, right? So instead of choosing between, LA and Burlington and New York City based on some populations, and so there'll be a third each. You choose an individual from the US and then look at their city. What it means is that is in terms of a model, it's incredibly simple. You don't have to think about groups at all at any point. Right? As you make this thing run, you don't think about groups at all. And they're not really thinking about it either, right? These groups aren't really, banding together or anything. It's just this long ticker tape. And after the fact, you can start to group them and count them up. Yep, good. So it's a rich-get-richer story. There's a competition between the individuals, and that's random, right? Between the individual ones is random, right? So the competition between any of these individual words is random. These are all ooks, but this is a specific ook, right? It's here on the page. It's actually These are tokens. They are instantiations of ook. And you can think of them in terms of the ticker tape. Yes, this is yellow, but it's the yellow that appeared at time step 1. It has a, it's different to the yellow that appears at time step 7 in that sense. All right, so the competition between them is random, but the competition between groups is not as a result. So even though we never say anything about groups, the fact that we've got a whole bunch of yellows to start with, because they just kind of lined out at the front, means that they as a group can be seen to start to dominate. Of course, if we're talking about cities or we're talking about what, like there's all sorts of, there's grammar, there's how people move around, we would put all this kind of more realistic stuff into it. But there's no space. There's a one-dimensional space, sort of, but it doesn't. It's just time, right? There's just time. Okay, so we have group selection, and I should use the words type and token in here. I don't really put that. Sorry. At some point, I'll get it more uniform. So it's biased by size. Random selection, in this, it seems easy, right? I mean, it's easy for you to do it with code, right? At this point in time. If you wanted to do it by groups, if you only knew about the groups, then you'd have to say, well, okay, I need to know how many people live in that city, or how many. If you didn't kind of have this access to all these words, all you know is, actually, there are 33 these and 44 ands and so on. Then you'd have to do this calculation, right? So it's different. If they've been grouped together, then you have to say, oh, I know what all the probabilities are, and I have to roll this weird die to kind of select from it. And you can imagine this working, say, for cities in terms of population, because migration or movement between cities, like someone, right, in Des Moines, and so they're your friend, and you're like, okay, I'm moving there because they told me things. You're not sampling from all of the world, right? There's sort of a random connection, sort of. Okay, so that's an issue. Like, do you need in these simple models, is it asking for some like omniscient knowledge, like, sort of facility in terms of, what's being chosen? As I said, earn models, Polya appeared, right, for the random walk stuff. I regretted calling him a genius, even though I suppose people will say that. Irons and colored balls, funny business. Okay. Yeah. It's a sampling problem. We create a sampling problem, we replace things back in, and then we put in some new colors now and then. One big urn in this case. You have lots of urns, lots of balls. Yeah. Let's see what this gives me. The urn problem, yeah. Really does feel like a 1920s thing. Yeah. Yep. Yep. Everyone's excited about this. Yep. Hypergeometric distributions, the binomials, lots of things. Okay. Okay, so we've just set it up like this. We have one new elephant per unit time. So that's a total number of elephants, right? So our population is growing, 1, 2, 3. Our population at time t is just t. The distinct number of flavors, or if you like, cities or words, is growing at this rate rho. That's not actually how, if you say, look at words, new words appearing as you read through a book, and I had this scaling in the scaling slides at the very start, like that's called Heap's law, and it rolls over, right? There's sort of a power involved there that rolls over. That would be true if you were sampling, like organisms are coming at you, you're going through a forest and just randomly sampling organisms. Lots of ants, lots of ants, lots of ants, lots of ants. Lemur, like blah, 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 right? And you just have this little list of and you're counting up how many you've seen of each kind. And then if a new kind appears, you note that. That would also tend to roll over. That's not what we're doing here. We have a steady rate. So there's a linear growth of new things. All right, fine. Simple model doesn't quite do all the right things. We could do that, and that would be a game of like changing that rate of introduction.
It just seems like to me in that example with the book, the row would decrease over time. That's the case.
Yeah, so that's right. So because you want the number to grow as a sublinearly. That's right. I kind of feel like someone must have done that, but Simon's model is very famous, but I feel like it wasn't examined super deeply for a long time in some ways because it's 50s. The computer stuff kind of came later. A lot of people got a lot to do. And then the network thing took off. It was connected back to it, but it's like networks, yay. So that would be a good, that would be a natural thing to try and make it a little bit more like you're still going to have random words appearing, right? It's not like a real written thing, but it would have more of a character of how things are introduced, right? And you should be able to see it for cities, say in the US, right? I mean, just take it, or Australia or somewhere, where we have data on recent development of, so Europeans coming in and building these places. The rate at which there's an amazing study actually of post offices, going back to the 1700s in the US, and visualization, you can see them, appearing and then disappearing as cars come along. Okay, but you could add a few other things, right? So sometimes the color will go away, which would be like a word falls out of usage. Maybe a city, goes away, or a city becomes smaller. The population goes down. You could move between the groups, right? So elephant could, paint itself a different color, go to a different place, or soak itself in something, marinate to get a different flavor. It's really not good. Really should have stopped. Okay, so again, please don't eat elephants. So I can't stress that enough. So previous classes, some things have gone wrong. So variable innovation rate, which is what we've talked about. But I think a nice, a natural one would be to try to get that Heaps law behavior. And again, different. You could do group size selection, like move away from the random thing. But then this is going to be, as I said, it's going to be a difficult thing because now you need to know all the group sizes, and now you have to do some, kind of calculation about which one you want to join. You sort of a weird things like I will think of all the cities in the US and weight them in funny ways. We try to do it. It's true, we try to do it. I did hear about this. I first came across this actually. It's this large Venezuelan volleyball playing maniac gave me this book at the Santa Fe Institute, and it's Krugman has this little book, The Self-Organizing Economy. It's a bit silly. So he has this chapter. It's quite small, but he's like, Simon showed in a completely impenetrable exposition that the exponent of the power law distribution should be. All right. So you guys will, overcome that. Krugman obviously was a bit too much. Anyway, he gets a Nobel Prize, but it's okay. Gamma functions. Alvaro Cartea. Yes, long time ago. Yeah, I know it has pies in it. I don't know why people will use pi. All right, but they do. So, and actually, I when I was a graduate student, there was a year where Krugman was at MIT for a year. I don't know what happened. They went to Princeton or something, and I wrote an email to him about this paper. I thought it was interesting because it's a long time ago. It was hard to, like, if you want to track down a paper, you had to really. And I don't think the reference was right or something. Anyway, he replied and said, yeah, he was excited about it. He said, but he felt like he didn't like the rho going to zero limit or something as well. Anyway, whatever. So it was sort of funny, like these things appeared in my view, and I feel like, I mean, that doesn't mean they're right, but eventually over time you start to see they had bigger and bigger, and they were appearing in lots of different places. And of course, the network story we'll get to later on, just an enormous space. But this rich-get-richer phenomenon, I mean, it's just everywhere in some way. Okay, so how do we try to do some analytics for this? And let's set it up. So we're gonna have we do analytically have to kind of travel between these two different spaces a bit. While the simulation is really easy, analytically we're actually going to try to think about groups because that's what we want to get at. We want to get at the group size. So we have I groups, and you know, we could think of them as just having the numbers 0, 1, 2. They can be just, they're labeled like that. We don't have to think about colors. We can say there's group 1, group 2, group 3. Start at 0 if you want. I know this is a thing that people get excited about. So this is going to be the number of groups, and so this is our zip story, right? The number of groups that have k elephants at time t. So we have to think about this in the long-term limit. You know, it's not obvious to start with that this could end up as a big mess. Like, it's not clear at all that this ends up with some parallel tail. It will, but, you know, we don't know that. Right, so we want to know how this thing evolves. So we're going to set it up there are different ways to approach this problem. It turns out the one Simon used, which I'll outlay here, misses this first mover. It just can't get it. Because the first mover is is off the distribution. It's a delta function kind of story. And an approach which actually turns out to be similar to what Barabasi and Albert did, which, you know, we wrote up in a paper here, gets you all those very specific details, because it says, what about, you know, what about, it really focuses in on the number of times that it looks at the ticker tape and says exactly like how many times does this one get reproduced. So we're going to smush them together a little bit more. All right, so we have to figure this out. What's the probability that this new elephant comes along and chooses a group of size k to belong to? Well, we know we have this many groups of size k. We're just saying this, right? And this number, right? So there'll be, in general, there'll be a group that has many, right? So there'll be one of those. And then as we go down, this is Zipf's law kind of story, right? Or size frequency sort of thing. Eventually, we'll get to the number of groups that are of size 1, so there'll be many of those. So this is to try and get back out to our randomness thing where we're saying, well, we're going to choose from any of these, we're going to replicate any of them. This is the number of groups of size k, and if we multiply by k, that's how many elephants are in those groups in total. Right? So what we're doing at this point is we're saying, you know, groups of size 1, they're all different flavors, but we're going to count, you know, we're now sort of stepping back and saying, oh, all we want to know is how many groups are of size 1. We're not going to talk about their different flavors. We know they have different flavors. But in terms of the mechanic of the thing, this is what we need to know. So, as I said, we have T elephants overall by this point, and so this is the probability that we choose a group of size k for our elephant to join. So again, this is the number of elephants in size k groups, and there are T total elephants. So this is the fraction of elephants that are in size k groups. So 1, right, there'd be just 1 times M1T up to whatever the maximum group size is. So that's our probability of attachment. So this is the same kind of structure as what we had before. The number of groups will change. The number of groups with k elephants in them will change if one of those groups gets one more elephant in it, right? So that's one thing that can happen, because now it's a k plus 1 size group. So if you have one of those groups is a little replication inside it, well, now it's in the k plus 1 category. So the other thing that could happen is a group that's a bit smaller, it's got k minus 1 elephants in it, it gets a replication inside it. Now it's in the k size group. So there are two things that can happen. So this is the number of groups of size k at t plus 1 decreases, right? So we lose one, and this is going to happen with this probability. So first of all, this is the probability of replication, right? Because mutation happens probably rho, so we have to have that piece. And now this is the probability that we replicate, and this is the probability that we choose a group of size k. or a city of size k. On the other hand, we're going from one of these groups of size k minus 1, got an extra 1 inside it. That adds 1 to our number of groups of size k. Now, this is exciting. Again, it has to be because we're talking about replication, so not mutation, replication. And in this case, we've chosen a group of size k minus 1. And so that has to be a k minus 1 and a k minus 1 here, right? This is a number of groups of size k minus 1. They all have k minus 1 in them. Multiply that together. So this is a number. This is actually a number as well, right? It's the number. It's the total number of elephants. So now we've got our two pieces that can help us change, that help us, manufacture an equation for change. If we look at the number of groups of size 1, that's a bit different. It has to be the new elephant is a new flavor, right? So that's just, we get a new one, and it gets, a new elephant comes in, it's a flavor we haven't seen before, so of course the number of groups of size 1 is increased. That simply happens with probability rho. You don't have to do anything else. And then this looks like what we had before, where a group of size 1, so as an elephant, gets a friend. It doubles, right? So it goes bloop. So it goes to a group of size 2. Again, that can only happen if there's replication, and that we choose a group of size 1. So this is really 1 times m1t divided by 2. I know. So I think we can put these things together. So this is there's a little bit of sneakiness happens here, right? So this is the expected change in the number of groups of size k, going from time t to t plus 1, right? We're going to have we have to have replication, and then we get these two pieces. There's a plus 1 and a minus 1. So we're losing one if a elephant in a group of size k replicates, and we're getting one more if a group of size k minus 1 becomes a group of size k. And then we have to have a special one for k equals 1. So this actually looks the same. If we put k equals 1 here, k equals 1 here, that's the same piece. But then we just have a completely different piece here. You can't put this in. So this is, right, this doesn't collapse back to this. This is just a plus rho. And it's really plus 1 times rho. So probability that you innovate, and then you have a plus 1. That's how many you get. And again, this is the number of groups of size 1. The unique ones, the hapax legomena, the rarest that we have. So this is our analysis. And it's a bit, this is an expected change. And what you kind of hope is that this is roughly true, because this is for size k. Of course, we've got size k, 1, 2, 3. We've got lots of sizes. We've got all of these equations, right? There's one equation here, but we have all of these parallel equations. And it's just expected value. But the rough thing that we do now is we start to say this looks a bit like a derivative, right? So if we put a t plus 1 minus 1 on the minus t on the bottom, right? That would be the time here and the time here. Then we get just a 1. So this is kind of like change in number times change in time. So we approximate that with a derivative. Could be a terrible thing to do, and sometimes these things don't work out. But that's going to be the game. So we want to see, we're going to assume a couple of other things. So if this works out, it really does get to something stable, then it can't depend on time. It can only grow linearly with time. So we kind of want to see this distribution just grow. Because if it's not stable, it's going to be wafting all over the place, right? So this is a presumption. If it doesn't work out, then we have to start all over again. It's a bit weird. We have fractional numbers of elephants, but we're thinking about long time scales and average behaviors, maybe across different ensembles. Okay. And we don't really need this too much now, but this is going to be a useful thing when we think about the fraction of groups that have size k. So this is the Let's just leave that for now. All right, so we're going to replace these more, in principle that have size and time mixed in. It's just going to be this little n sub k. There's no time in this thing. This is a sort of big universal we're trying to get to. That's times t plus 1, not a function of times t plus 1. And then this is minus little nk times t. And you can see those things are going to cancel here. So we're going to turn it into a difference equation, right? This is sort of a way of going. We could have gone to a differential equation. This is going to a difference equation. There are some shenanigans we can put in. So again, this one here, this is going to be n, little n k minus 1. This is just a product. This is just a product. So now we've got a simple, well, I may not think so, but we have a simple problem, right? We're just going to group these things together, t plus 1 minus t, so that's this piece. The t's cancel. The t's cancel over here as well, right? So we made an assumption, we're carrying it forward, and the game is to see, do we get a result that then, holds up? So we rearrange a few things. I know there's some, this is just nk times 1 at this point. There's a 1 minus rho times minus kn sub k, so we're going to, we'll pull that over in a second. This is just cleaning things up. This is nk times 1 minus rho. These are cleaned up. So we can see we can bring this blob over to this side. That's what we'll do. So it's nk times 1, and there's a minus 1 minus rho k over here. So that's what this piece is, that red piece there. And then we've just left this over here. 1 minus rho, k minus 1, nk minus 1. 1 minus rho, k minus 1, nk minus 1. So all of that blob goes to there, and this blob comes to this side. All right, so this is algebra. Doesn't really explain, the thing that you look at and think this is hopefully informative is this. I mean, you have to, we've written out in a certain way so you can kind of read off what the terms are, right? This is a probability, this is a change in size, etc., etc. Algebra time, we're working through it, and now we've got nk blob times nk minus 1. So we can rearrange that, and now we've got this little recursion thing. So it's nk, and we can think of blob times nk minus 1. So this becomes the thing to play with. So we can start with, n of little n1, whatever that value is. Then we can make n2 and n3 and n4. The k's are just the numbers, right? Go 1, 2, 3, 4. And then the row is whatever you've fixed and whatever you've chosen at the start. This all falls apart if you have rho equals 0 or rho equals 1. You have to go back and do the analysis again. They are, we know what they are, right? So if rho is 0, there's no innovation. You just copy the first one, right? You just end up with all of them being the same. If rho is 1, everything is different. They're the extremes. And maybe if you work with limits, you'd be okay. All right, so we'll just finish this page, I think. So we're interested in what happens for large K, right? Tail of the distribution. What's weird is, that's our natural interest. What's weird is it will also work out for K equals 1, 2, and 3. So we'll get both ends of this distribution, which is a really surprising outcome. So this can be solved exactly. This is the game. It's in the paper, and we'll sort of work through it. It's a tiny glitch in one of their expressions. It's not assignment 4, obviously. You can just get the tail, expand in terms of 1 over k. That's another problem. And this is what you would end up finding. That the number of groups of size k decays as k to the minus gamma. Like, this functional form pops out. So that's the first thing. And then that the exponent is this 2 minus rho over 1 minus rho, which we can rewrite as 1 plus 1 over 1 minus rho. So this is this thing. So if we dial it towards 0, right, this becomes close to 2, which is that extreme limit, right? This is something where the mean is becoming infinite. As we dial rho towards 1, this becomes 1 plus a large number. So the tail becomes thinner and thinner and thinner. So it gives us an enormous range of outcomes, right? The really extreme fat tail, not 3 halves, but 2 back to sort of almost infinity, right? Which is a weird power law. But it all depends. It's all governed. So there's a little toggle in here, which is a little variable at the start. So we have a microscopic model. It has this one parameter that we dial, the row, and from that we get out a whole family of macroscopic behaviors. So there isn't a universal story here in the sense of, it gives you 3 halves or something like that, right? It actually gives you a spectrum. And then you can start to think, well, maybe I can measure this row, and you'll do that for Pride and Prejudice and Ulysses, right? Those books aren't written like this, but you can measure this row, like what's the innovation rate, and then see if you get a reasonable estimate. So it's a model that's wrong in lots of details, but it'll be surprisingly effective. Okay, so we'll talk more about it on Thursday, and then we'll get to Mandelbrot. Office hours will be Wednesday and Thursday, I think, yes. All right, thank you, sorry. Okay. Gotta work on these TikToks.